Hello everyone, my name is Santosh and I am a student of BSc Chemistry Honours, second year. It's an audio video lecture on chemical bonding and molecular structure. Scientists are constantly discovering new compounds, orderly arranging the facts about them, trying to explain with the existing knowledge, organizing to modify earlier views or evolve theories for explaining the newly observed facts. Matter is made up of one or different type of elements. Under normal conditions, no other element exists as an independent atom in nature except noble gases. However, a group of atoms is found to exist together as one species having characteristic properties. Such a group of atoms is called a molecule. Obviously, there must be some force which holds these constituent atoms together in the molecules. The attractive force which holds various constituents together in different chemical species is called a chemical bond. Since the formation of chemical compounds takes place as a result of combination of atoms of various elements in different ways, it raises many questions. Why do atoms combine? Why are only certain combinations possible? Why do some atoms combine while certain others do not? Why do molecules possess definite shapes? To answer such questions, different theories and concepts have been put forward from time to time. These are Lewis approach, valence shell electron pair repulsion theory, valence bond theory, molecular orbital theory. The evolution of various theories of valence and the interpretation of the nature of chemical bonds have closely been related to the developments in the understanding of the structure of atom, the electronic configuration of elements, and the periodic table. Every system tends to be more stable, and bonding is nature's way of lowering the energy of the system to attain stability. Lewis' approach to chemical bonding. In order to explain the formation of chemical bond in terms of electrons, a number of attempts were made, but it was only in 1916 when Kozel and Lewis succeeded independently in giving a satisfactory explanation. They were the first to provide some logical explanation of valence, which was based on the inertness of the noble gases. Lewis pictured the atom in terms of positively charged kernel and the outer shell that could accommodate a maximum of 8 electrons. He further assumed that these 8 electrons occupy the corners of a cube which surrounded the kernel. Thus, the single outer shell electron of sodium would occupy one corner of the cube, while in the case of a noble gas, all the 8 corners would be occupied. This octet of electrons represents a particularly stable electronic arrangement. Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. In the case of sodium and chlorine, this can happen by the transfer of an electron from sodium to chlorine, thereby giving the Na positive and Cl negative ions. In the case of other molecules like Cl2, H2, F2, etc., the bond is formed by the sharing of a pair of electrons between the atoms. In the process, each atom attains a stable outer octet of electrons. Lewis symbols. In the formation of a molecules, only the outer shell electrons takes part in a chemical combination and they are known as valence electrons. The inner shell electrons are well protected and are generally not involved in the combination process. G. N. Lewis, an American chemist, introduced simple notations to represent valence electrons in an atom. These notations are called Lewis symbols. For example, the Lewis symbols for the elements of second period are given here. Significance of Lewis symbols. The number of dots around the symbol represents the number of valence electrons. This number of valence electrons helps to calculate the common or group valency of the element. The group valency of the elements is generally either equal to the number of dots in Lewis symbols or 8 minus the number of dots or valence electrons. Kozel, in relation to chemical bonding, drew attention to the following facts. In the periodic table, the highly electronegative halogens and the highly electropositive alkali metals are separated by the noble gases. The formation of a negative ion from a halogen atom and a positive ion from an alkali metal atom is associated with the gain and loss of an electron by the respective atoms. The negative and positive ions thus formed attain stable noble gas electronic configuration. The noble gases have a particularly stable outer shell configuration of 8 electrons, Ns2 and P6. The negative and positive ions are stabilized by electrostatic attraction. For example, the formation of NaCl from sodium and chlorine according to the above scheme can be explained as Na gives rise to Na positive plus 1 electron. Chlorine plus 1 electron give rise to chlorine negative. Na positive plus Cl negative give rise to NaCl or Na positive Cl negative. The bond formed as a result of the electrostatic attraction between the positive and the negative ions was termed as the electrovalent bond. The electrovalence is thus equal to the number of unit charges on the ion. Thus, calcium is assigned a positive electrovalency of 2, while chlorine a negative electrovalence of 1. Cosell postulations provide the basis for the modern concepts regarding ion formation by electron transfer and the formation of ionic crystalline compounds. His views have proved to be of great value in the understanding and the systematization of ionic compounds. At the same time, he did recognize the fact that a large number of compounds did not fit into these concepts. Octet rule. Cosell and Lewis in 1916 developed an important theory of chemical combination between atoms known as electronic theory of chemical bonding. According to this, atoms can combine either by transfer of valence electrons from one atom to another or by sharing of valence electrons in order to have an octet in their valence shells. And this is known as octet rule. Covalent bond. Langmuir refined the Lewis postulations by abandoning the idea of stationary cubical arrangement of the octet and by introducing the term covalent bond. The Lewis-Langmuir theory can be understood by considering the formation of chlorine molecule Cl2. The chlorine atom with the electronic configuration neon 3s2 3p5 is 1 electron short of the argon configuration. The formation of Cl2 molecule can be understood in terms of the sharing of a pair of electrons between the two chlorine atoms, each chlorine atom contributing 1 electron to the shared pair. In this process, both chlorine atoms attain the outer shell octet of the nearest noble gas, that is argon. The dots represent electrons. Such structures are referred to as Lewis dot structures. The Lewis dot structures can be written for other molecules also, in which the combining atoms may be identical or different. The important conditions being that each bond is formed as a result of sharing of an electron pair between the atoms. Each combining atom contributes at least 1 electron to the shared pair. The combining atoms attain the outer shell noble gas configurations as a result of the sharing of electrons. Thus, in water and carbon tetrachloride molecules, formation of covalent bonds can be represented as. Thus, when two atoms share 1 electron pair, they are said to be joined by a single covalent bond. In many compounds, we have multiple bonds between atoms. The formation of multiple bonds envisages sharing of more than 1 electron pair between two atoms. If two atoms share 2 pairs of electrons, the covalent bond between them is called a double bond. For example, in the carbon dioxide molecule, we have 2 double bonds between the carbon and the oxygen atoms. Similarly, in ethene molecules, the 2 carbon atoms are joined by a double bond. When combining atoms share 3 electron pairs, as in the case of 2 nitrogen atoms in the N2 molecule and the 2 carbon atoms in the ethene molecule, a triple bond is formed. Lewis representation of simple molecule, the Lewis structures. The Lewis dot structures provides a picture of bonding in molecules and ions in terms of the shared pairs of electrons and the octet rule. While such a picture may not explain the bonding and the behavior of a molecule completely, it does help in understanding the formation and properties of a molecule to a large extent. Writing of Lewis dot structures of a molecule is therefore very useful. The Lewis dot structures can be written by adopting the following steps. The total number of electrons required for writing the structures are obtained by adding the valence electrons of the combining atoms. For example, in CH4 molecule, there are 8 valence electrons available for bonding, 4 from carbon and 4 from hydrogen atom. For anions, each negative charge would mean addition of 1 electron. For cations, each positive charge would result in a subtraction of 1 electron from the total number of valence electrons. For example, for the CO3 2 negative ion, the 2 negative charges indicate that there are 2 additional electrons than those provided by the neutral atoms. For NH4 positive ion, 1 positive charge indicates the loss of 1 electron from the group of the neutral atom. Knowing the chemical symbols of the combining atoms and having knowledge of the skeletal structure of the compound, it is easy to distribute the total number of electrons as bonding shared pairs between the atoms in proportion to the total bonds. In general, the least electronegative atom occupy the central position in the molecule ion. For example, in the NF3 and CO3 2 negative, nitrogen and carbon are the central atoms, whereas fluorine and oxygen occupy the terminal positions. After accounting for the shared pairs of electrons for single bonds, the remaining electron pairs are either utilized for multiple bonding or remain as the lone pairs. The basic requirement being that each bonded atom gets an octet of electrons, less represents of a few molecules given in a table. Formal charge. Lewis dot structures in general do not represent the actual shapes of the molecules. In case of polyatomic ions, the net charge is possessed by the ion as a whole and not by a particular atom. It is, however, feasible to assign a formal charge on each atom. The formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of valence electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. It is expressed as formal charge on an atom in a Lewis structure is equals to total number of valence electrons in the free atom minus total number of non-bonding lone pair electrons minus half of total number of bonding or shared electrons. The counting is based on the assumption that the atom in the molecules owns 1 electron of each shared pair and both the electrons of a lone pair. Let us consider the ozone O3 molecule. The Lewis structure of O3 is given as the atoms have been numbered as 1, 2 and 3. The formal charge on the central oxygen atom marked 1 is +1. The end oxygen atom marked 2 having charge 0. The end oxygen atom marked 3 having charge -1. Hence, we represent O3 along with the formal charges as 1 oxygen having plus charge, the center, 1 end oxygen have negative charge and 1 end oxygen don't have any charge. We must understand that the formal charges do not indicate real charge separation within the molecule. Indicating the charges on the atoms in the Lewis structure only helps in keeping track of the valence electrons in the molecule. Formal charges help in the selection of the lowest energy structure from a number of possible structures for a given species. Generally, the lowest energy structure is the one with the smallest formal charges on the atoms. The formal charge is a factor based on a pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. Limitations of the octet rule. The octet rule, though useful, is not universal. It is quite useful for understanding the structures of most of the organic compounds, and it applies mainly to the second period elements of the periodic table. There are three types of exceptions to the octet rule. The incomplete octet of the central atom. In some compounds, the number of electrons surrounding the central atom is less than 8. This is especially the case with elements having less than 4 valence electrons. Examples are LiCl, BH2 and BCl3. Lithium, beryllium and boron have 1, 2 and 3 valence electrons respectively. Some other such compounds are AlCl3 and PF3. Second one is odd electron molecules. In molecules with an odd number of electrons like nitric oxide NO and nitrogen dioxide NO2, the octet rule is not satisfied for all the atoms. The third reason is the expanded octet. Elements in and beyond the third period of the periodic table have, apart from 3s and 3p orbitals, 3d orbitals also available for bonding. In a number of compounds of these elements, there are more than 8 valence electrons around the central atom. This is termed as the expanded octet. Obviously, the octet rule does not apply in such cases. Some of the examples of such compounds are PF5, SF6, H2SO4 and a number of coordination compounds. Interestingly, sulfur also forms many compounds in which the octet rule is obeyed. In sulfur dichloride, the sulfur atom has an octet of electrons around it. Other drawbacks of octet theory. It is clear that octet rule is based upon the chemical inertness of the noble gases. However, some noble gases also combine with oxygen and fluorine to form a number of compounds like XeF2, KrF2, XeOF2, etc. This theory does not account for the shape of molecules. It does not explain the relative stability of the molecules being totally silent about the energy of a molecule. Ionic or electrovalent bond. From the causal and Lewis treatment of the formation of ionic bond, it follows that the formation of ionic compounds would primarily depend upon first, the ease of formation of the positive and the negative ions from the respective neutral atoms. Second one is the arrangement of the positive and the negative ions in the solid, that is a lattice of the crystalline compound. The formation of a positive ion involves ionization, that is removal of electrons from the neutral atom, and that of the negative ion involves the addition of electrons to the neutral atoms. The electron gain enthalpy is the enthalpy change when a gas phase atom in its ground state gains an electron. The electron gain process may be exothermic or endothermic. The ionization, on the other hand, is always endothermic. Electron affinity is the negative of the energy change accompanying electron gain. Obviously, ionic bonds will be formed more easily between elements with the comparatively low ionization enthalpies and elements with comparatively high negative value of electron gain enthalpy. Most ionic compounds have cations derived from metallic elements and anions from non-metallic elements. The ammonium ion NH4 positive is an exception. It forms the cation of a number of ionic compounds. Ionic compounds in the crystalline state consist of orderly 3D arrangements of cations and anions held together by Coulombic interaction energies. These compounds crystallize in different crystal structures determined by the size of the ions, their packing arrangements and other factors. The crystal structure of sodium chloride and NaCl, for example, is given hereby. In ionic solids, the sum of the electron gain enthalpy and the ionization enthalpy may be positive, but still the crystal structure gets stabilized due to the energy released in the formation of the crystal lattice. For example, the ionization enthalpy for Na positive formation from Na is 495.8 kg per mole, while the electron gain enthalpy for the change of chlorine into chlorine negative is minus 348.7 kJ per mole only. The sum of two 147.1 kilojoule per mole is more than compensated for by the enthalpy of lattice formation of NaCl, and that is minus 788 kilojoule per mole. Therefore, the energy released in the process is more than the energy absorbed. Thus, a quality measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not simply by achieving a state of electrons around the ionic species in gaseous state. Since lattice enthalpy plays a key role in the formation of ionic compounds, it is important that we learn more about it. Lattice enthalpy. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. For example, the lattice enthalpy of NaCl is 788 kJ per mole. This means that 788 kJ of energy is required to separate 1 mole of solid NaCl into 1 mole of Na positive gaseous and 1 mole of Cl negative, that is gaseous, to an infinite distance. This process involves both the attractive forces between ions of opposite charges and the repulsive forces between ions of like charge. The solid crystal being 3D, it is not possible to calculate lattice enthalpy directly from the interaction of forces of attraction and repulsion only. Two factors associated with the crystal geometry have to be included. Bond parameters. Bond length. Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Bond lengths are measured by spectroscopic, X-ray diffraction and electron diffraction techniques, about which you will learn in the higher classes. Each atom of the bonded pair contributes to the bond length. In the case of a covalent bond, the contribution from each atom is called the covalent radius of that atom. The covalent radius is measured approximately as the radius of an atom's core, which is in contact with the core of an adjacent atom in a bonded situation. The covalent radius is half of the distance between two similar atoms joined by a covalent bond. In the same molecule, the van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bonded situation. Further, the van der Waals radius is half of the distance between two similar atoms in separate molecules in a solid. Covalent and van der Waals radii of fluorine are depicted here in a figure. Some typical average bond lengths for single, double and triple bonds are given hereby. Bond lengths for some common molecules are also given. Bond angle. It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or a complex ion. Bond angle is expressed in degree, which can be experimentally determined by spectroscopic methods. It gives some idea regarding the distribution of orbitals around the central atom in a molecule or a complex ion, and hence it helps us in determining the shape. For example, HOH bond angle in water is 104.5 degree. Bond enthalpy. It is defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. The unit of bond enthalpy is kilojoule per mole. For example, the hydrogen-hydrogen bond enthalpy in hydrogen molecule is 435.8 kilojoule per mole. Similarly, the bond enthalpy for molecules containing multiple bonds, for example O2 and N2, will be O2 is 498 kJ per mole and N2 is 946.0 kJ per mole. It is important that larger the bond association enthalpy, stronger will be the bond in the molecule. For a heteronuclear diatomic molecule like HCl, we have 431 kJ per mole. In case of polyatomic molecules, the measurement of bond strength is more complicated. For example, in case of H2O molecule, the enthalpy needed to break the two OH bonds is not the same. The difference in the enthalpy value shows that the second OH bond undergoes some change because of the changed chemical environment.